In this video, we discuss the foundations of valence bond theory. Valence bond theory is a modern theory to explain covalent bonds that goes beyond Lewis-dot structures and VSEPR theory. Remember that Lewis-dot structures and VSEPR theory actually do not require a quantum mechanical description of the electrons that are shared in a covalent bond, okay, because they precede the advent of quantum mechanics. Valence bond theory utilizes all that we know about quantum mechanics to try to explain how bonds are formed in a covalent compound. All right, so this is the essential tenet of valence bond theory. Suppose that you think about the easiest molecule that there is, H2. All right, when we draw the Lewis-dot structure, essentially what we have is this. Okay, you have two atoms that they are sharing two electrons, and that's what forms the covalent bond. Okay, but again, there's no quantum mechanical description of the electrons in that bond. Now we can try to see how valence bond theory then explains that sharing of electrons. The idea is very simple. You just take the atoms separated, H and H, and then look at their electronic structure, electronic configuration, right? So one is one each. So the idea here is that you have orbitals that are singly occupied. Okay? And it is that, well, these orbitals, these wave functions, then can overlap, okay, much as waves do, to form a bond, right? So the way to draw a valence bond theory diagram for H2 would be something like this. Here you have a separated H atom, that is the 1s orbital, and it has one electron. And then here you have the other H atom, the 1s orbital representing the 1s wave function for that electron. And again, when they're very separated, those two atoms do not interact. But then you can bring them together, and those atoms can interact. Okay, and those wave functions can overlap. Okay, we can write them like this, right? Given a region of space in which both electrons can be at the same time and be attracted simultaneously by the two atoms, right? So it's essentially this overlap of the orbitals that generates a bond. Notice that once that bond is formed and you have two electrons there, the Pauli exclusion principle forces those electrons to have antiparallel spins. Okay, so let's repeat this concept. The idea of valence bond theory is that a bond is formed by an overlap between the atomic wave functions between two atoms. Okay, now, so there's some requirements for these bonds. First, you cannot have more than two electrons in the region of space where the overlap takes place, because that would be a violation of the Pauli exclusion principle. And if you have two electrons being shared, then the spins of those two electrons have to be antiparallel. And again, that is to not violate the Pauli exclusion principle. Now, something interesting about this bond is that if we look at the molecule from this side, right, along the internuclear axis, which will be this axis, we actually see that this bond has what we call cylindrical symmetry, okay? And that is what we call a sigma bond, okay? Sigma bonds are those that have cylindrical symmetry around the internuclear axis. All right, so that is the example of H2. We're going to do a couple more examples here for the illustration of valence bond theory. Let's try to do here HF. All right, so HF, now it's going to be this molecule, HF. All right, or we can just write it like that, and then try to draw here the Lewis-dot structure. Too long here. Right, that will be the Lewis-dot structures, and then try to figure out here what the electronic configuration for fluorine would be, which is helium, and then 2s2, 2p5. If we draw the box electronic configuration, it will be something like this. For the valence, it will be, this is the 2s, and then we have 3 2p's, and you have 5 electrons, so 1, 2, 3, 4, and 5. All right, so within the context of valence bond theory, bond is formed when two wave functions overlap so that there is no more than two electrons in between the two atoms in that region of space, and those electrons have to have antiparallel spins once the bond is formed. Right, so when we think about these orbitals that the fluorine atom has and the orbital that represents the electron in the hydrogen atom, we can clearly see that the overlap is going to be produced between these two orbitals, right? Notice that you cannot form an overlap between that orbital and either one of these, because that would give you a total of 3 electrons in the same region of space, and that would violate Pauli's exclusion principle. All right, so now we can, with this knowledge that the overlap is going to be formed by these singly occupied orbitals to have two electrons in the central region of space in between the atoms, then we can go and draw try to draw how that valence bond theory diagram would look like for HF. All right, so here you will have H, right? That is one as wave function with one electron, and then here you will have F, and then F you can say, well, that is the 2s orbital, 2 electrons. Okay, we're not going to draw the core orbitals because they do not participate in bonding. And then you have, if we call this the x axis, that will be the 2p x-axis, and you have 2 electrons. And then you will have an orbital coming in and out of the plane, which will be perpendicular to the 2px. We're going to call that the 2py. It's very difficult to draw in 2 dimensions this orbital coming in and out of the plane, so we're actually going to draw it at an angle here. Okay, so this to us would mean coming in and out of the plane. We label that as 2py, you have 2 electrons, and then we have to draw the 2pc, which I'm going to draw as directly overlapping with that 1s wave function of the hydrogen atom, 2pc, and then 1 electron, and that is your bond, right? So in HF, according to valence bond theory diagram, the bond is formed by the overlap of the 1s wave function of hydrogen with one 2p wave function of fluorine that is singly occupied. Okay, that gives you 2 electrons in the same region of space. Now these 2 electrons can be simultaneously attracted by fluorine and hydrogen, and that is what forms a covalent bond. Okay, when we think about the symmetry of the electronic density around that bond, again, if we look at the molecule from this angle, we can see that there's cylindrical symmetry around that bond, so this is also a sigma overlap. Okay, so notice how we can now establish similarities and differences between Lewis dot structure and then valence bond theory. Lewis dot structure, we have that there's a single bond, okay, where 2 electrons are being shared, and that is exactly what we have in valence bond theory, but we have much more details about how that overlap takes place, right? We can actually figure out what the orbitals in the overlap are, right? The other thing is that here we have lone pairs, right? And now we know where those lone pairs seem to reside in the case of fluorine, right? So you have 2 lone pair as being part of the 2s orbital, then the other 2 lone pairs are part of the 2px and 2py orbitals, which are not involved in bonding. Okay? All right, so that is a little bit more of valence bond theory. We're going to close this discussion of foundations of valence bond theory by trying to come up with the valence bond theory diagram for the nitrogen molecule. All right, so let's see if we can do that quickly here. Nitrogen. Okay, you draw the Lewis dot structure for reference, and that has a triple bond, and then 2 lone pairs on the nitrogens. Okay, so the first thing that we do in valence bond theory is write the electronic configurations. Right, so that is going to be helium, 2s2, 2p3. Okay, we draw the box electronic configurations, that is the 2s orbital, and then these are the 2p orbitals, and according to Hund's rule, that will be the lowest energy electronic occupation. Of course, for the other nitrogen, you're going to have exactly the same. Helium, 2s2, 2p3, and then draw the box electronic configurations, and this is what you find. That is the 2s, and this is the 2p. So when we look at these electronic configurations, then we can ask the question, what type of singly occupied orbitals are going to overlap here? And you can clearly see that the 2s are not going to be able to overlap, because that would place too many electrons in the same region of space, and that violates the Pauli exclusion principle. However, now we have that there's 3 singly occupied orbitals in each of these 2p sets, which seem very ready to form overlaps and form bonds, right? So it looks like we're going to have here overlaps, 3 of them, and we just have to draw them to see how they actually look like. All right, so we come to drawing the diagram. That will be nitrogen. This is your 2s orbital with 2 electrons. And then we have the 2p set. Okay, so that is to the 2p c orbital. Arbitrarily, I'm assigning the z direction to this axis. And then also arbitrarily, I'm assigning this axis to be the x direction. And then you will have the y-axis coming in and out of the plane. which we're going to draw here at an angle. Okay, so that is 2py, then each one has 1 electron. Okay, this will be the orbital representation of that electronic configuration. Now, what we have here is the other nitrogen atom, which has a similar electronic configuration, right? That is the 2s orbital, and then you're going to have now a 2pz orbital right here, okay, which has 1 electron, and once the overlap is formed, those 2 electrons have to have antiparallel spins. Okay, let me withdraw this. Okay, there's a ring of overlap right there. Okay, so that will be one of your bonds. It's an overlap between singly occupied 2pc orbitals that places 2 electrons with antiparallel spins in the same region of space, and that is a bond. Okay, but then we also have something else. We have that the 2px right here is also singly occupied, right? So notice the question that we have here is whether these orbitals that are singly occupied can also form a covalent bond, even though they're not overlapping head-on, right? So the answer is yes. You can actually have this overlap, okay, between these 2 singly occupied orbitals, so that the 2 electrons are in between the nuclei right here and form a covalent bond. Okay, notice that the overlap here is very interesting, right? Notice that it's not head-on, as you have here with the 2 PCs, but instead it's going to be side-on, right? So that overlap is going to have the 2px overlapping in between the nuclei right here, okay, but it has a slightly different symmetry than what we actually have for the 2 PCs, right? So again, when we go back to the symmetry arguments, look at the internuclear axis for this overlap between the 2 PCs that has cylindrical symmetry, that is what we call a sigma bond. But if you now look at the electron density around this overlap in the 2px axis that doesn't have cylindrical symmetry, okay, that instead is what is called a pi bond. Okay, all right. So an easy to see difference between these 2 orbitals would be the fact that this is a head-on overlap, but this one is a side-on overlap. Okay, so that is a sigma bond, and that is a pi bond, or a sigma overlap and a pi overlap. Now, this is not the end of the story for nitrogen. Notice that in this atom, you still have a 2py orbital that is coming in and out of the plane, and it also has only 1 electron. Okay, so you're also going to have a side-on overlap with the same 2py orbital from this atom, right? So again, notice that you have 2py orbitals that are singly occupied, and they can overlap side-on. Okay, so we can draw this simply as this, right? There will be an overlap, and that is the overlap, that is the 2py. And if you look at the symmetry around this overlap, you will see that that also is not a sigma. Instead, it happens to be a pi. Okay, so we now have a beautiful description of how the bonding in nitrogen is according to valence bond theory diagram. Okay, what we see is that there's 3 overlaps between singly occupied orbitals of each atom. One of them is a sigma overlap, and 2 of them are pi overlaps. Okay, so we can now try to reconcile what we actually saw here from Lewis-Dot structures, right? Lewis-Dot structures told you that you have a triple bond, but there was no understanding of the quality of those bonds. In valence bond theory, you can quickly learn that one of these happens to be a sigma overlap, and then 2 of them are actually pi overlaps. Okay, so you augment your understanding quite easily. Okay, so this has been an introduction to the foundations of valence bond theory, and the key concept there is that bonds are formed through overlaps of atomic orbitals.